In this video, we're going to review vectors and scalars. So scalars have magnitude only. So in the context of fluid mechanics, examples of scalars would be things like pressure. So for example, a pressure of 150 kilopascals, or density, the density of a fluid. So for example, the density of water could be 1,000 kilograms per meter cubed, or even specific gravity. Specific gravity does not have a direction associated with it. It is simply, it's unitless, and it's just a magnitude. So in contrast to these scalars, we have vectors, which do have both a magnitude and a direction. So for example, we encounter vectors quite a lot in fluid mechanics. So an example would be a fluid jet leaving a nozzle with a velocity of 5 meters per second to the right, which we'll say is along the positive x-axis. So here we have both a magnitude and a direction, which qualifies this as a vector. So vectors can, of course, be broken down into their components. So they can be broken down into perpendicular parts called components. So, of course, the number of components depends on if you are in 2D or 3D. So in 2D, of course, you'll have X and Y components. And in 3D, you'll have X, Y, and Z components. And why do we need to break things down into components? Well, this makes it quite easy, much easier when we're doing things like applying Newton's second laws, for example. So working with components, makes it easier to do things like add or subtract vectors, apply Newton's laws, etc. So how do we find these components? Well, so finding components. So we'll suppose, for example, that we have a velocity vector which has a magnitude of capital V and direction of theta. And we'll draw this here as an example. We have our velocity vector here, which has this magnitude of V. And we can break this down into the x component. Right, where Vx is equal to V cosine of theta. So we have our x component here, Vx. And then we have our y component right here. And the y component is Vy is equal to V sine of theta. So x component is V cosine of theta, and the y component is V sine of theta. And we'll do a quick example here. So we'll say that we have a water jet leaves a nozzle V equals 20 meters per second at 30 degrees above horizontal. So in this case, we can find the components. So V sub x will be the magnitude, so 20 meters per second times cosine of 30 degrees, which is 0.866. That gives us 17.3 meters per second. And the y component, Vy, would be 20 meters per second, the magnitude of the velocity vector, times sine of 30 degrees, which is 10 meters per second. And so we could also write this as V is equal to 17.3 I, which indicates the x direction, plus 10 J, and this is in meters per second. So that tells you the x and the y component. Now we can also add vectors using components, and we'll look at that briefly as well. So adding components to add vectors. So here we'll say that if we have some vector, which we'll call A, and A has an x component, which we'll call A sub x, acting in the I direction, plus A sub y, the y component acting in the j direction, or the j component here. And if we have a similar vector, which we'll call B, which similarly has x and y components, bx and by, then in that case, if we want to add those two vectors together to make some resulting vector, then that vector would be r is equal to a plus b. And then we can add these two vectors together by adding the components. So we would say that the components of this new vector r are r sub x, which is equal to a sub x plus b sub x, and r sub y is equal to a sub y plus b sub y. If we want to then find the magnitude of that resultant, we would simply use the Pythagorean theorem and say r is equal to the square root of r sub x squared plus r sub y squared. And finally, the resultant direction we could find as theta is equal to arctan of r sub y over r sub x. And that is generally with respect to the positive x-axis.